I saw a lot of questions in the chat about, what is, what are the differences between reward modeling and how do you actually verify the outputs are correct? So I'm hoping that as we work through this case study, piece by piece, it'll become very obvious, how you can formulate, reinforcement learning style ideas through this GRPO algorithm that DeepSeek came out with. Cool. So to set some context, right, the goal we're trying to solve for today is, can we teach an LLM how to convert PyTorch code, right, into functional, accurate, and optimized Triton or CUDA kernels? Now, for those who aren't familiar with what CUDA kernels are essentially functions that are purpose-built to run on GPUs. And the reason that they're very interesting is that they can run many small computations in parallel all at once and then combine the results or some combination of that. And usually these are really, really fast to run on GPUs compared to, doing something that's not so optimized. And CUDA kernels are typically written in something called like CUDA C or CUDA C++, which is extremely low level. So for people who work in, as data scientists or machine learning engineers, unless you have deep expertise, it's a pretty difficult problem, write yourself. And so there's an alternate called Triton. Triton is essentially a compiler that is able to compile down to CUDA C and CUDA C++ for you. But the really nice thing about Triton is that it's actually written in Python. So it has the Python API. You can express that logic of GPU programming in something that you're comfortable with, and leave it to Triton to compile it down into something that can run on CUDA. Right, that's the high level idea. And I'll show you what that looks like in a moment. But the reason this use case is very interesting is that, there are many cases where you might want to transpile code between, convert Java to Python or Python to C, C++, right, like this. Or there are other use cases like an enterprise where, we've seen a lot of people and a lot of companies that have, natural language to code generation for some sort of workflow. Things like that. And so a similar formula can be applied for those tasks as well. Now, to show you what this looks like in practice, right, here's an example of a simple two-line PyTorch function, or a function that uses torch, and it's called silu in place. And all it's doing is it's computing the silu activation function on a tensor in place, which is a very common operation in deep learning these days, especially in large language models. I won't dive into what's actually happening in the torch function, but what you can imagine is we have this piece of torch code. We want to give it to an LLM, and we want the LLM to generate this large blob of output code. And what this code is, so this code actually represents a Triton kernel that is functionally equivalent to the PyTorch code on the left, but it is significantly faster in its execution, right? And you can see that, I know that most of us here are not GPU programming experts. Maybe have never heard of Triton. Maybe have never heard of CUDA kernels. So we don't need to focus on the specific details. But I think that the point I'm trying to get at is that it's a pretty challenging task to get right, even for humans who are experts in the field, let alone an LLM. Now, as I alluded to earlier, writing CUDA kernels requires deep GPU programming expertise. There's people who spend lots of time writing these kinds of things. And the interesting challenge about this is that most people know how to write things at the level of Python, at the level of PyTorch. But when you execute PyTorch code by itself, it's often suboptimal. And so you're wasting GPU resources. So it makes sense to actually have a way to write these optimized CUDA kernels. And so, that's one of the challenges with this task. And the second is that, why it becomes interesting is that when you move to different pieces of hardware, so H100, H200s, like the GH200s when they come out, or I think they're already out, a lot of these kernels, like each of these have different GPU architectures. And so you want to write kernels that are leveraging the hardware characteristics, and, hand optimizing these each time is time consuming and error prone. So it would be pretty nice to just have PyTorch code and then send it to an environment and have it learn how to optimize it for that architecture, right? So yeah, that's like the high level idea. And what I did want to emphasize is, like, normally when I see tasks like this, I think about supervised fine tuning, which is what Travis was talking about earlier. it should be a good fit for a task like this. But unfortunately, one of the most interesting problems is that there is no open data set for a task like this, even though people are interested in it. And so, supervised fine-tuning is unlikely to work well because we don't have enough data. And so that's actually where, a task like this is now possible through this new idea of reinforcement fine-tuning. And here's here's why actually this task in particular is a really good fit. The first is that we obviously lack a large data set and one that has input and output pairs, so it's labeled. But with reinforcement learning, because it's an online algorithm, I'll show you what that means in a moment. You can essentially just hand curate 10 examples by yourself and create a data set out of that. And that is enough to get started, right? Very, very simple. The second is that because we're writing code, code is inherently verifiable, right? And it's objectively verifiable in that code always executes the same way most of the time, right? And in our case, what this means is that we could have something write kernels and then maybe write something like test cases, run it against the code and see if it compiles and produces the same output. So we have a mechanism that we can devise to basically grade the quality of the output that the model is producing. And the third is that, large search spaces, this problem is like, it has many different solutions because you can go all the way from getting it correct to optimizing different parts and, for different matrix sizes. And there are analytical solutions, but it requires very deep expertise. But reinforcement learning balances this idea of exploration, which is what are the different things I can do, with exploitation, which is what is consistently working really well. And reinforcement learning should be able to explore the search space in a very smart and efficient way compared to, how we might do it. So all of these make it like a really good setup for reinforcement fine-tuning. So hopefully the problem statement is clear and people know what we're trying to solve for. So let's dive into methodology and learnings. So when you're constructing a problem like this and you want to run it through reinforcement fine-tuning with GRPO, the DeepSeek formula, there are two key components you need to construct: a data set, at the very least, with some prompts. And the second, and these prompts, ideally they're well structured, there's a bit of diversity, but what you're really looking for is very high quality inputs, right? Just 10 is sufficient. And some sort of diversity so the model can learn a generalized strategy to solving your problem. And the second part is the verifiable deterministic reward functions. And I know people have many questions about this, and I'll show you what it looks like 2 slides from now. But the idea is that, since you don't have a ground truth to compare to, you need a way to at least tell the model in some capacity whether it's doing something correctly or not. And you want to be able to do that in a very objective way so that every time the same output is produced, you give it the same score and there's no non-determinism. So it knows for a fact that this is like the score it's going to get. And by keeping it objective, we eliminate noise, should help train the model faster. So let's talk about how we would create a data set for this task, because that's what we had to do, right? So when it comes to data set creation, here's the easiest strategy that you can think of for a task like this. This is what we did. We went to GitHub, a treasure trove for open source code that lives out there. And we searched through a bunch of open source repositories that have some sort of Triton kernel implementations. And there are actually quite a few that have, people practicing, just like how to write Triton kernels, to people actually like using Triton kernels for their specialized tasks, so on and so forth. And what you can do is you can actually like grab these kernels out from these code repositories that are open source, and you can run them. And what's really nice is that most of the times people write like a PyTorch equivalent and then a kernel equivalent, and then write a test case to show that the output is the same. So you can verify that it compiles and the kernel is valid. Now, once you have that, remember, this is actually sort of like the output, right? But what we want is an input we can pass to the model to actually generate these kernels. So what you can do is one of two things from there. I did like mostly the first, which is convert the Triton kernels to Torch code yourself. Or if they have Torch code in these repositories for these kernels, then copy them over, fix them, modify them to make it make sense. But if you're not an expert, we can always send it to, let's say, like Llama 370 billion and have it generate the PyTorch code for you, and then you can modify and fix it as you want. And then finally, to make sure that our Torch code is correct and our Triton code is correct, we can write some test cases, run it through both, and validate that all test cases pass through both. So we know the Torch code is equivalent to the Triton code. And what's really nice about doing it this way is that your test cases can also be used during training to verify correctness. And we'll come to that and I'll show you what that looks like as well. So our training set is just 13, I want to be clear, like 13 examples that have like a system message and this PyTorch code. I showed you a snippet in the first slide. And the goal is basically to tell the model to write, equivalent Triton kernel. So now that we have our data set sort of handcrafted this way, it only took me like 30 minutes or so to get this there, or maybe an hour. The second part is how do we now write verifiable deterministic reward functions? And a really good framework to think about reward functions is you want to do two things. So the first is that, and DeepSeek also kind of followed this formula, and it's very understandable why now. So the first is that you want to write a formatting reward function, and the idea is that you want to do two things with it. The first is give it some knowledge on, what a good solution might contain. And the second is give it some sort of format so that you can extract out the answer and then verify it, right? If it's very open-ended, you don't know what part of the generation to look at to verify. But if you tell it like, hey, put your answer between answer tags or put your answer between code tags, then you can look for that in the output, extract it out, and then verify correctness. So the first is the format reward function, and the second thing you want is a correctness reward function, which is actually telling it like, hey, was this answer correct? Yes or no. So in our case, when we first took a stab at this problem, we decided to go with 3 reward functions, 2 for formatting and 1 for correctness. So this is an example of a reward function. And as I said, there's 2 interesting properties about it. It is deterministic, deterministic, programmable, and verifiable. So what I mean by that is for each generation that the model produces for a given prompt, we can say, hey, do you have the Triton code / Triton code tags present in the output, right? And that's done through this like regex match written over here. So we take the completion, do regex match, and say, if you have one instance of this exactly, then great, you get a reward of 1. Otherwise, you get a reward of 0, right? So the idea is that over time, it will probably try to produce these tags, and we'll tell it to do that in the system message. And whenever it does actually produce this, we'll say, you did well, like here, you get a reward of 1, others you get a reward of 0. And this is what we're going to look for to extract our code out to then execute it later, right? So we wanted to learn this pretty quickly. The second is, a Triton keyword reward function. Just very simple. It's almost trivial. I'm checking if it's just importing the right Triton packages, because we know that is the first set of lines that are required to actually write a valid Triton kernel that will execute. And so it just does string matching, like is triton.jit in completion, import Triton in completion, or import Triton language STL in completion. And if all 3 are true, which are required, then you give it a reward of 1, else you give it a reward of 0, right? And again, hopefully during its early exploration phase, it will try this by itself and get those rewards and then use that as signal to do this continuously. So these are 2 format reward functions that we wanted to learn. And then the third thing, as I mentioned, is the correctness reward function, right? And it was a lot of code, so I didn't put it here. But this is sort of like a flow chart that describes what's going on. So for each completion, we follow like a multi-step process. We say, hey, are there Triton code and / Triton code tags present? If not, we return 0. But if yes, we can extract that code out from those 2 tags, right, using regex matching. And then we check, hey, do you have an entry point function, basically a regular PyTorch function that we can call and pass in the test case values? And does that invoke a kernel call internally? Yes or no, right? And you can do that by loading the code into a module and doing some interesting massaging and parsing. So if it doesn't have that, then we know that this cannot be a valid kernel to begin with, because those are the 2 things we wanted to do. Let's say it gets that right as well. The third step is to load this code, right? We know it's valid, run the test case in a new Python interpreter on a GPU, and then capture the output value. Now, 2 things might happen here, 3 things really, right? It might throw an exception, which means that, there's a compile time error or a runtime error because Triton kernels are just-in-time compiled, in which case it will return an error of 0. But in case it doesn't throw an error, it might either get the answer correct or wrong. So if it gets it correct, it will return a reward of 1. Otherwise, it will return a reward of 0, right? So it's a very simple way of verifying, right, that it's learning something and that it's doing the right thing. And this is an example of like a correctness reward function. So this is what we took a stab with and kicked off training. And oh yeah, sorry, I should probably also talk about system and user messages. So how does it know to produce these like Triton code tags, or hey, like make sure you have an entry point function and a kernel function? You actually use your system message and your user message to tell it that. And so, here's an example of like our system message and our user message initially. You'll notice that there's no think tags here. It turns out that this model doesn't need to think to do this task. In fact, it gets worse when it thinks, and that happens sometimes. It's just task dependent. But yeah, just wanted to show you that there's something like this. So with all of this, we can kickstart our reinforcement fine-tuning training loop. And, we start with our frozen model. We take a prompt, right? We send it to Lorax, which is our open source serving framework. And we have it generate n different completions for the same prompt. And this is done with temperature-based sampling so that there's some difference between each prompt that's produced. We pass those to a reward server, and the reward server takes the completions and produces rewards from each of the reward functions for every single generation, right? So format is scored separately from the Triton formatting, which is scored separately from correctness, and those scores are sent back to the model server. The model server looks at that, calculates something called advantages, which is which generations were better than the average and which generations were worse than the average. And then the weights are updated. So your LoRa weights, we use LoRa-based fine-tuning. It updates the weights. And then what we can do is send this new checkpoint to Lorax again and say, hey, here's the next prompt. Can you generate n more completions? So it's this online learning process where you're utilizing the latest model every single time. And we loop over, 13 data points over and over and over again in this fashion. And here are some of our initial observations. So what I have here is like 3 different sets of learning curves. There's the rewards, the format reward function on the top left, the Triton format reward function on the top right, and then the correctness reward function on the bottom left. And there's 3 observations we can make from looking at this. The first is that by training step 100, both the formatting reward functions actually have, are nearly right 90% of the times in all the generations they produce. That means that it's actually learned to produce our formatting quite well by this point, which is great. Right? It's a sign of learning. Like it is learning how to get it through trial and error, through exploration. The second is, as we approach the 100th step, where formatting is finally correct, you'll notice that there's a pretty steady increase in the frequency of getting the correctness right of our test cases. And that makes sense, right? Now you have all the right imports. You were able to parse out the code clearly. And it's learned how to do that for all of our examples pretty well. And so now it's able to actually run our test cases through, and it's learned over time through trial and error what at least, compiles and can run without errors. And then, yeah, sometimes it gets a lot of things right. So you'll see these spikes, which basically said got both of our test cases right. So it's an emergent property that comes as part of like the training process over time. And the third is very interesting too, which is that the correctness reward takes much longer to learn than the formatting rewards. But I will say it is actually learning faster than I expected, because on our test set, it produced a score of 0 out of the box. So it should take much longer to learn how to get it right. And so the question then is that it? Does that just work? Do we just let it train and does it get everything right over time? Maybe. We should also look at, individual outputs that are being generated and assess whether it's doing the right thing, right? So again, there's a lot of code and text on the screen. We don't have to focus too much on it. But what I wanted to show you is on the left is the Triton kernel that was actually generated by this model. And on the right is the ground truth Triton kernel that I got from GitHub. And you'll see that functionally, they're almost exactly the same. Just some edge case handling that's missing in terms of like how you write and read from memory. So great signs, looking pretty good. But the more time we spent, we spent with these generations, it became obvious that it's, not always so good. So here's another example where on the left, it's a summation kernel, just sum along dimension one in a tensor, produced by the model, and on the right is the ground truth. And one really funny emergent property of reward functions like this is that it can lead to something called reward hacking. So this kernel is actually completely wrong. And it's wrong. It's wrong in that it actually gets 100% of the test cases right, but it does it because it found a clever loophole to our reward functions. What it's doing, in a sense, is no matter what's happening in the kernel, at the end, it calls x.sumdim equals 1, which is just the PyTorch implementation that always works. So it basically wrote a dummy kernel function that does nothing, but it found a way to maximize reward anyway. And this is actually a very common phenomenon in reinforcement learning, where the model comes up with a very clever way to work around the reward functions to maximize it. And so, this was an example of an undesirable behavior because this effectively doesn't do anything, but it passes and gets maximum reward. And so, as we analyze this further and further, here's an example of what's supposed to happen, but we can skip past it. There are other emergent challenges. I saw that it keeps invoking invalid Triton methods, or tries to load them from the wrong library. It learned how to exploit test cases where the output is just a tensor with zeros because it just skipped the kernel call and just returned like torch.zeros. Very clever. And in our rewards, if you see how we define those, they were all either you get a score of 1 or a score of 0, right? So you don't provide any partial credit for partially correct outputs. If it compiles, it should get some signal that it's made progress, but we only tell it it's doing something at the end when it gets something right or wrong. So learning is slower and it can go a bit more rogue in its exploration because of that. And that's called like having reward signals that are too sparse. And yeah, having only 2 test cases means that the reward signal is also very sparse, and I'll talk about that a bit more in a couple of slides. So from this first pass, we can see that it's directionally doing something. It's showing promise, but it's obviously not nearly where we want it to be. So in general, reinforcement learning with this style of strategy with GRPO is sort of iterative in that you need to look at the reward curves, look at your reward functions, and look at what the model's generating, and based on that, make changes and keep improving your reward functions. And so we wanted to solve for all of these challenges as well, and we went through several iterations. So I'm going to show you what we came up with in the final iteration now. We did this over a week. The first is that we use a much more comprehensive system message. The first thing we did is added an explicit sort of like part of the system message that tells it all the valid functions in the Triton.language module so that it hallucinates less in producing invalid functions. The second is telling it how exactly to invoke these functions. So you can do like tl.method name, and that will work. But it doesn't know what arguments get sent into the function. It just knows this function exists, right? So kept it simple. And the third thing is we want to solve for reward hacking, and I'll tell you like the actual process. But we tell it that the output buffer, like the place where it should generate the output from the kernel, should be the first argument it sends to the kernel and be called output. And this is the artificial format that we are enforcing so that we can verify that it's doing the right thing, right? And I tell it like, hey, use torch.zeros or torch.full specifically to initialize these buffers for specific reasons. So updated system methods giving it even more context clues because it's struggling to get it right, or it tries to hack it without these, which is totally possible. The second is actually improving the format reward function. So we're going to do like a couple of different things. We're going to, one, merge our 2 format reward functions into one. The second is that we're going to expand the list of reward criteria by being even more specific about what is good and what is bad based on our learning so far. The third is that, so let me show you what that looks like. Are the Triton code tags present? Does it use the imports? Does it use only valid methods from the Triton language library? Does it use torch.empty? Does it use load and stores properly? Some other signs that, it's using the kernels the right way or setting them up correctly. And the third thing is, yeah, we can assign partial credit. So the idea is that as you expand the list of criteria, right, for it to get a score of 1, it has to get everything right if you just have binary reward scores. The odds of it getting that is very low, right? It's going to have to like luck out and get all of those things correct. So it doesn't have much signal to learn like what to try next. But by giving it partial credit in this fine-grained way, it knows that this is slightly better than this, and this is slightly better than this, and it can use those increments to head towards the right direction where it gets all of these things correct. And the second thing is we can also introduce negative rewards. Like, hey, we want to discourage this behavior. So if you're doing all of this right, but this wrong, I don't want to give you full score because it's a behavior I don't want you to do. So that is also something you can do as well. And we found that this actually helps push it towards the right behavior that we want. And then you sum these and you get a total reward, and you do this per completion. So it's still very fast and cheap to do. It's just, string matching really, or regex matching, pretty fast. So much more expanded reward function. And then there's a much more expanded correctness reward function. And I know there's a lot of text on the screen, but what I want you to focus on is the two dotted arrows, or right here. This is the original reward function that we wrote, but what we want to solve for is checking for reward hacking. And the easiest way to do that is to, once your kernel, so the model produces a kernel, we ran it through a test case, and it produced a value. And it looks like the value was matching what we want, the expected output. To make sure that the kernel is actually responsible for doing the logic, what we can do is that we can monkey patch the actual kernel the model produced with the artificial no-op kernel that does nothing, right? And then we can check the output from that call. And what we would hope is that if the outputs match, then it's a bad sign, because it means that the the function that's not the kernel is doing all the work, like we saw in that example with the reward hacking. So that's actually bad, and we want to give it a score of 0. But when the outputs differ between when we use the kernel and when we use the no-op kernel, it means that the score was entirely produced by the kernel, which is a great sign. That means it's doing all the logic using pure Triton. And for that, we're going to give it a reward of 1. So it's a special guardrail mechanism that we built to check for reward hacking, and you can use these ideas in other code examples as well. And the third thing is, as I mentioned, 2 test cases are rather sparse, right? When you have 2 test cases, it means you can only produce 3 reward values per generation. A score of 0, which means both test cases are wrong. A score of 0.5, which means 1 out of 2 test cases are right. And a score of 1, which means both test cases are right. But when you expand out the test cases to 4, you actually get much more fine-grained reward values, which again nudge the model in going towards the right direction, right? Instead of having more sparse values. Ideally, you would do 8, 12, 16, or 32 test cases, but obviously you need to spend the time to write those out, because that would give you much more continuous, less sparse reward. But for now, we just doubled our test cases from 2 to 4. And finally, if you're still with me, we also decided to give some partial credit for compilation, separate from correctness. And all it's doing is, hey, if you can run the code and it doesn't throw an error, you get a reward of 1, even if the output value is wrong, because it helps nudge it towards the right direction, given that the correctness reward is now much more complicated, right? So we want to give it some sort of intermediate value to use to go towards the right solution. So yes, to summarize, 3 things: much more improved and comprehensive format reward function. We update our correctness reward function to check for reward hacking. And we add a compilation reward function to give it partial credit when it can write functional code, even if it doesn't execute correctly. It doesn't produce the right answer at the end. And when we run it this way, we ran this for like 5,000 training steps, so much longer. There's, again, a couple of key observations that we can make, right, from doing it this way. The first is that we only start to see it getting 90% of the generations at, high success rate at 1,000 steps compared to 100. So it's spending a lot more time getting the formatting right, because it has to actually update its strategy to get there. And so yeah, definitely, like, the rules we enforced made it much harder for it to get formatting right, but it means that it had to change the way it tries to greedily solve this problem, at least in my mind. The second is that once we hit this 1,000th step, or when we start to approach it, you'll see that compilation reward starts to spike as well, right? This partial credit of like, hey, you wrote functional code that doesn't throw errors. But correctness reward basically stays 0 until we start to see high format scores and high compilation scores, because At that point, it starts to optimize for correctness and no longer for like compilation or reward functions. It finds that there's another way to maximize reward. And the third is that is correctness, which is, accuracy peaks at 2.5. Is that basically it goes through these like uh, these variations where it starts to optimize for correctness, then it starts to optimize for compile because it thinks that if it optimizes for compile, it will get higher correctness. And then we'll see at the at the tail end of the correctness reward function between step 4,000 and 5,000, it starts to spike up again. So, positive signs that it's learning something. And just to show you, again, we're not Triton experts here, but to show you examples of what this model actually produced, I'm going to highlight just a couple of quick things. It decided that it should add doc strings. To me, that's almost like its internal chain of thought to get to like a right solution. It correctly initializes the output buffer with the constraints that we have. It correctly like only passes an output to the kernel and returns the output directly. So it doesn't do any torch function invocation in this part of execution. And within the kernel itself, it does a lot of like really positive behaviors, which I won't get into, but like lots of good signs that it's doing the right thing. And these kernels are correct; they actually work. Similarly, here's another one to calculate outer product. Won't go too into it, but a lot of very similar signs. It learns, you can calculate block size ahead of time, use torch.zeros, just pass in the output and have the kernel do all the work. So it's a much more involved kernel because it operates on two 1D CUDA tensors and yeah, gets it right as well. So it definitely like learns a lot more with these evolved reward functions. And there's obviously like things that to be done. When we ran this on the test set, now we're seeing like 40% accuracy, where it gets all test cases right on the test set, and then about 50% accuracy on 3 more of those examples, and on 3 it just gets it completely wrong. So what I want to highlight with that is that if you look at these curves, you can see that's roughly around 40% accurate. And that translates really nicely to the test set as well, because it doesn't know how to mimic. It learned the strategy for solving, which is what makes RL so powerful. And other things we can try next, scale up generations for faster convergence, increase the number of test cases to get even more granular rewards. And one thing we didn't optimize for is efficiency of the kernel, but you can imagine we can add a reward function for runtime where you run the torch code, you run the kernel, and you do like a distribution of time it took to execute. And then the bigger the difference between the torch and the kernel, the higher the reward, right? So you optimize then for not just writing correct kernels that get the right answer, but also using optimizing for efficiency as well. And that is something that it's verifiable in that it's correct and you know it's runtime. So lots of good stuff there. And with that, I know I have just a few minutes left. And we spent the past month working on this Triton to Torch to Triton use case, logic QA, countdown, and all of these other tasks. And we spent a lot of time figuring out, what are the pain points in getting this process working smoothly and nicely, what kind of tooling you need to actually make decisions quickly to help your models reach the performance that makes sense and that is very promising. And we decided to take all of those learnings and basically build it into our product because, we understand like where this process is difficult. And I think that's where really, like, I think for RL style training, managed solutions are going to be more attractive than ever. Right. So just to give you a glimpse of what that looks like in the product, or what it's going to look like in the coming weeks. Normally, when you land into the database UI, we have both the UI and an SDK. You can pick between supervised fine-tuning and completion style fine-tuning. We're going to add a new task type called GRPO. And when you select that, you can pick, you can connect your data set to dropdowns, pick a base model. So you can use any of the DeepSeek models, but you can also use any of the non-reasoning models. This recipe works on those as well. Right? And you can configure trainer parameters such as epoch learning rate, adapter rank, so on and so forth, right? So lots of different things that you can do there. And when we train, we're going to show you these reward functions, like very similar to the ones I showed you. We show you on a per step basis, so you can see what it's learning and how each of those individual rewards are progressing, as well as the overall cumulative reward. And as you saw, it's very useful to see where it's struggling, what the trends are, and what the patterns are, because that gives you a lot of information. in addition to just seeing like the rewards, we're also going to let you see the completions being generated per step of training, which is actually incredibly helpful in seeing like what the model's finding as a strategy, like the aha moment that people talk about. They look at the generations themselves. I mean, we found our reward hacking through this. So you can filter to any of the prompts or pick a random prompt. You can look at all the generations for any given training step. And you can even, filter by a step to see how it's changed over time. Let's say like it's seen it for the 10th time. What is it doing now that it wasn't doing before? Which is incredibly powerful because we know that this kind of information, like being live during the training process, can help you make really smart decisions about what needs to change. And in case you're more of a Python first person, don't really like a UI first experience, we also are building this into the SDK. And it's as simple as these many lines of code. So you can specify your base model, your trainer parameters, LoRa parameters, and then you can pass on a list of Python reward functions. And the idea here is that we want to let people customize how they assign reward so that they can train this for all sorts of tasks, which is sort of like a different approach compared to like the way OpenAI has been thinking about it. And you don't have to pass in reward functions. We will default to essentially doing exact matching and seeing if the exact matches are working. So this should give you full flexibility to actually reproduce our experiment with Torch, like the Torch of Triton, or Countdown or Logic QA, but also go really crazy with things like talking to a Notion, like it's a Notion connector and verifying like things there, or taking code, running it through your SQL database if you're doing text to SQL optimization. Yeah, basically the full-fledged, like you can design your reward functions as you desire, and we will execute them.